what I wanted to try to show you here is a simulation of the Earth and how the Earth experiences the intense radiation from a solar flare, and how our magnetic field does the best it can to try to protect us, even under these kind of adverse circumstances. And so here we see the intense output of solar wind coming in from the sun during a solar flare. And you notice how the Earth's magnetic field is weathering the storm somewhat, but it's still, of course, difficult to handle the kind of radiation that is being produced during a solar flare event. Okay. And so next, what I wanted to do is talk a little bit about the evolution of stars in general. First of all, when we think in terms of the typical kind of a solar system that we might run into, we often think that, well, maybe this is a lot like our own solar system, because this one is familiar to us, and so why shouldn't they all be like ours? But no, that's not the case. Turns out that at least 50%, maybe more like 60% of stars that we can see are part of binary star systems. Or more. Could be tertiary or quadruple star systems. And so our solar system is in the minority, only having a single star with planets going around it. However, that turns out to be a good thing for the Earth. Because if we were, in fact, in a multiple star system, this would tend to destabilize the orbits of planets. And so without having a stable orbit around a single star, we are much less likely to have a habitable planet. I'm not saying that we can't have a double star system and still have advanced forms of life. It still is mathematically possible to set up a planet so that it's in an orbit around a star that's a double star system. But we haven't found any planets so far that are habitable in multiple star systems, okay, or that are even close to being habitable. And so it cuts down your possibilities considerably. And so we might then wonder, well, why did our solar system end up as just a single star system? A couple of possibilities. One is that we did have a binary companion, and it was torn off by some huge catastrophic event that could have occurred as another star passed nearby, or something like that, when the solar system was first forming. Another possibility is that Jupiter would have been our binary companion. Only about 10% of solar systems have a big planet like Jupiter. So it's somewhat unusual. It's possible that Jupiter just got outcompeted for material, and that's the reason why it's a big planet instead of a small star. And so that, in fact, is another possibility. But when we look at a typical star system, what you might have are, say, two stars orbiting around each other, which is to say that the two stars look like they're going around and around each other like this, but in reality they're both orbiting around a common balance point, or center of mass. And this is also true for the Earth-Moon system. it isn't just the moon going around the Earth and the Earth staying stationary. It's actually the Earth and the moon both orbiting around a common center of mass. Turns out the center of mass for the Earth-Moon system, it's actually, the balance point is actually inside the surface of the Earth. And so what it gives rise to are tidal bulges instead of the appearance of the Earth and the moon both going around each other. Okay? And so this is the kind of thing then that is normal then for multiple star systems, is to have two stars going around each other. And this tends to make planet orbits less likely. So we didn't really even include this in our probability calculation for the possibility of extraterrestrial life. But we should have. This is actually in our miscellaneous category. Everything else that we didn't talk about. This would be one of those other things that the majority, we think, at least, from what we can see, of other star systems are part of a binary or tertiary quadruple star system. And our single star system is much more conducive as a minority of stars are in our galaxy and in the cosmos to producing planets that have advanced extraterrestrial life. Okay, so what starts to happen then as a star goes through some of its states? Well, we still have a balance between the inward force and the outward force for any kind of a star. And so we looked at this picture before when we were talking about our own sun. But this is in fact the kind of equilibrium situation that all stars experience. And so when we're trying to determine what distinguishes one type of star from another, we really do have the same physics involved in our analysis, but just on different size scales. So we can have a smaller star, like what we would call a red dwarf star. A red dwarf might have a mass that might be equal to maybe 1/2 the mass of our sun. Okay, where M with a circle and a dot is the mass of our sun. Okay. But in this kind of a situation, you have inward forces due to gravity. You have outward forces due to fusion, reaction, just like before, but they're not as big. They're not as big. Why? Well, because there's less gravity compressing the core. And so a red dwarf star burns cooler. Because there's less gravity to balance out the force of nuclear fusion. The nuclear fusion is generated by heating of the core. So there's less heating of the core. And so this means then that a red dwarf star with a mass only half the mass of our sun is only using up about 3% as much energy as our sun is. And so it only burns about 3% as hot. So that might not seem like it would work out. If the mass is 1/2 the mass, you might think that it would burn 50% as hot. But no, it's a very strong dependence on the mass. And so it's really here the mass of the star that determines what is going to happen to it in the future. Because if it's only burning 3% as hot, then it can live a lot longer, even though there's less mass to begin with. So a star like this then could last maybe 200 billion years before it runs out of hydrogen. On the other hand, if we go to an intermediate mass star like our Sun, with a mass that's equal to itself, then our Sun is a bigger star, so it'll burn a little hotter because there's more gravity force heating up the core a little bit more. And with the core burning hotter, that pushes out harder, which is just what you need to do to balance out a stronger gravity force. So you need to crank up the furnace because you're pushing against a stronger gravity force. And so this is like our own Sun. And so the lifespan then of our Sun is something like 10 to 12 billion years, which is still a long time, but not nearly as long as a red dwarf. And so our Sun then is about half used up, and as time goes on it'll get less and less hydrogen available in the core, then finally it'll go into its end state of evolution in perhaps another 5 billion years or so. So that is still a long time. I've had students before that were quite concerned about that and asked me if I could repeat that, and I said, yeah, well, our Sun will probably last another 5 billion years. And they said, oh, what a relief. I thought you said 5 million years. But either way, we're not going to be around to see that. But that's what we think is going to happen eventually, is that our Sun will run out of hydrogen, and then we'll see what happens then a little later on in our lecture. Okay, so this is a normal Sun-like star, although our Sun isn't truly normal, because a star like our own Sun is probably in the top 10% in size, even though it's what we would call the normal range. There are a lot more stars that are less massive than our Sun than there are that are more massive than our Sun. But when we go to really big stars, and so here we might have a mass that's, say, equal to 20 times the mass of our Sun. This is what we would call a blue giant. And I'm not giving it justice here in terms of its size. A blue giant might be literally the distance from here to the planet Saturn. Okay, an all-star. Okay, and so it would have a mass, say, that's about 20 times the mass of our Sun, but the brightness or luminosity, how fast it's burning radiation, would be 80,000 times what it is on the Earth. And so the reason for that is that there's a very strong dependence on how much pressure is pushing in on the core, and how hot the core is, and how strong the fusion reaction is going to be. Okay, and so these big blue giants burn themselves out in a relatively short period of time, even though they've got maybe as much as 20 times the mass of our Sun. They may have a lifespan, burning hydrogen, turning it into helium, of only maybe 3 million years. Not billion, like is the case for our own Sun, or not 200 billion, as would be the case for a red dwarf. But for a blue giant star, we're looking at just a few million years. And so the motto then for these really big stars is live fast, die young. Because that's what they do. Okay, and so these kind of stars then, even though they are very fast burners and very short-lived, they tend to illuminate the arms of the galaxy, because these are the ones that put out so much more light than all the rest of the stars in the galaxy. And so these illuminate then the spiral arms because of their very, very large luminosity. That in terms of how long they can last, just a tiny fraction, maybe 0.1% as long as a sun like our own star, even though they start out with something like 20 times the mass of our sun. And so if we are to then look at a basic property of stars that determines its lifespan, its brightness, and the basic properties that differentiate one star from another, we'd say that it's mass. The mass of the star determines the star type and its lifetime. Even though it's the same physics for all stars, having that larger amount of mass disproportionately affects the brightness in the way that I've described here. Okay, but regardless of when the star runs out of hydrogen, eventually the core starts to age. So let me just go to the next stars. Let's find that in a second here. Okay, so here is the way that our sun looks if we look at the core structure now. What we see is an outer ring of hydrogen fusing material. Now when I say burning here, I mean hydrogen fusion and not burning the way that you burn something in a fire. This is just a very loose terminology in this case for hydrogen fusion. But in the center, we have non-burning helium. Okay, and so that helium is the waste product from hydrogen fusion. And so actually, this is why the sun is getting hotter with time. This is why we have to worry eventually about all of our oceans evaporating. And this is what happened to Venus, is essentially what is happening inside of the core. So here we have, for the case of our own sun, here's the outside regions of the sun. Here's the core. Here's the hydrogen. So we have here 4 hydrogen going to helium plus energy. That's what we loosely called hydrogen burning. But then here we have the inert helium core. Now, helium doesn't have much of a tendency to combine with anything else, and it's not hot enough for helium fusion to begin. And so this shell then, as time goes on, gets thinner as we run out of hydrogen. So as the star ages, the hydrogen burning shell gets thinner. And also more compressed. Okay, and so the heavier stuff then goes in to form the helium core, and the lighter stuff is still part of the hydrogen fuel but you'll eventually run out of hydrogen in the core. Does this mean you run out of hydrogen in the rest of the star? No. But it's just in the core where the temperatures are hot enough for hydrogen fusion to happen. So there's still plenty of hydrogen out here. It's just not hot enough for hydrogen fusion to happen out here. But in the core, we get more compression because of the helium center. The helium core pulls down on the hydrogen burning shell. And so you might wonder, well, what does that do? The answer is it makes it burn faster. And that heats up the sun. So this increases the brightness of the sun. And so put simply, the sun is getting hotter because of this. At a rate of about 10% every billion years. And so this is the reason then why Venus was once a habitable planet and is now experiencing a runaway greenhouse effect. And this is exactly what we're going to expect will happen with our Earth as the sun continues to get hotter. Eventually our oceans will evaporate. How soon will this happen? Well, depends a lot on us, maybe. And advanced life will end. How long will this happen? Will it take for this to happen? Well, we don't know. This is a big question mark. But we're using the Earth as a laboratory as we continue to pump more carbon dioxide into the atmosphere, which traps heat. Okay? And so we're basically doing this big experiment on the Earth, and we don't know what the outcome of this experiment is going to be. But eventually, the carbon dioxide will be removed completely in the process of our thermostat mechanism that we discussed earlier. But the sun will still continue to get hotter. So even with or without the carbon dioxide, or pulling it all the way out of the atmosphere, won't be enough to stop the oceans from evaporating. Once the oceans evaporate, life, at least as we know it, will end. Maybe some forms of life could still maintain themselves, but not the kind of life that we know about today. And so at that point, either we'll need to move the Earth, or it'll be time for us to find another home. Now we think of the Earth as being this really awesome, perfect garden paradise for life. But if we do a little clock here, where this is 12, 1, 2, 3, 4, 5, and each one of these numbers is a billion years, 9, 10, 11, then we've gone from basically 0 to 4.5 billion, and in the first 4 billion years there was just single-celled life. So if we go from the center here to 4 billion, this is single cell. Now let's say we're at 4.5 billion, so this is now. So let's say it goes until 5, or maybe a little over 5 billion before the oceans evaporate. this would be the beginning of multi-celled life. Then we're back to single-celled life again. And so it's just in this little tiny pie slice that we have advanced life. And so how much is this of the Earth's total lifespan? Well, maybe 1/12 or so. At the most, I think we could say maybe 10 to 16% of our total lifetime on the Earth will be multi-celled life, which I'll call advanced here. And the rest of the time, if an extraterrestrial were to fly by and go, nope, no advanced life here, this is not a habitable planet, move on. Nothing interesting here. So here the oceans have evaporated. So basically we're looking at single cell life or no life there. Single cell life, things were really hostile in the first 3 or 4 billion years of the Earth's existence. The moon was much closer to the Earth, generating gigantic tsunamis every time there was a wave breaking. It's like a 1,000-footer. And you had the Earth rotating more rapidly. You had you didn't have the ozone layer to protect us from harmful ultraviolet radiation, and so life had to exist in the oceans where it could protect itself from ultraviolet radiation in these early times. And then finally things settled down, and so we've got this kind of sweet spot here, this golden age for life that we're in right now, which is this tiny percent of the total amount of time that the Earth is around. And so when we think of the Earth as being this garden paradise, we have to realize that it's not going to last forever, and that it's really a very special set of conditions that allow for us to even be here now. Okay. But as time continues on, eventually we're going to run out of hydrogen. So all good things come to an end. So eventually, in the case of our own sun, this will be maybe another 5 billion years. But just in general, all stars eventually run out of hydrogen. So what happens then? Well, at that point, the star begins to die. And so you just have this helium core that's left without the hydrogen burning shell. Okay, so you just have the helium core, and then surrounding that you have the rest of the star. Okay? But once the hydrogen has stopped burning, there's no outward forces from fusion. Once the hydrogen in the core is gone. And so what happens? Well, the helium core experiences an unbalanced gravitational force because there's nothing to stop the collapse. So that means the helium core contracts more and heats up more. And so you can think of this as being a second collapse, because there was a first collapse too. When the star first formed out of the gas cloud, there was collapse number 1. And then eventually it found an equilibrium where the outward force due to fusion equaled the inward force due to gravity. and then it stayed there, in the case of our own sun, for maybe 10 billion years, turning hydrogen into helium. But then once that hydrogen runs out, then we have a second collapse. The helium core collapses, heats up more, and then eventually it heats up enough so that helium fusion can begin. Now remember, fusion means that the smaller atoms are being turned into bigger ones. Okay, so hydrogen fusion was the conversion of hydrogen into helium. And that was what was controlling the output of radiation of the sun during what's called its main sequence lifetime, which is just the main lifetime of the star. But then, near the end of its life, when it starts to die, helium fusion can begin. And so we can see a representation of that on the data projector here, where we look at the core. You have 3 helium atoms going to carbon plus lots more energy. And so this is happening now at a temperature in the core of about 100 million degrees. So you have a helium fusing shell. And that helium fusing shell is 3 helium going to carbon plus energy. But then that heats up the star even a little bit farther out, so that hydrogen that wasn't available for fusion is now available for fusion in a farther out layer. So this then is our hydrogen fusing shell, where 4 hydrogen goes to helium plus energy. So now we've got way more energy than ever before, because we've got not only a hydrogen fusion reaction in the outermost shell, but a helium fusion reaction in our inner shell. And then the waste product from that is carbon. Now, what are 3 helium nuclei added together with and connected by nuclear forces? Nothing other than the carbon atom. Carbon is element number 6 on the periodic table. Helium is element number 2 on the periodic table. And so 3 heliums and 1 carbon nucleus are the same thing. There's no difference between them. But it takes huge amounts of temperature. Okay, and so we're talking then about 100 million or more degrees Fahrenheit to make helium fusion happen. And so this occurred then because of the second collapse of the star as helium smashed down to create carbon. And then that generates more energy than ever. Why more energy than ever? Well, because there's more particles involved in each reaction, and it's a much higher temperature. So it releases more energy. And so now the whole star starts to lift up and expand outward, because the star was balanced for hydrogen fusion, but now we're generating more energy than ever. And so that pushes the star out. And so this is the beginning of the red giant stage. So during the red giant stage, the star expands. The outer surface of the star expands. In the case of our own sun, it will engulf Mercury and Venus, and maybe the Earth as well. And so this will happen, but it'll happen over a shorter period of time. Okay, so it might have taken, in the case of our own sun, 10 billion years for the sun to get to the point where it's ready to do helium fusion. But the helium fusion stage, the red giant stage, only lasts about 10% as long as the hydrogen burning stage. One to 10% as long as hydrogen burning stage. Why is this true? Well, because it's burning hotter and there's more particles per reaction, and so you're running out of fuel faster. Okay, and so it's an accelerated reaction, but you're running out of fuel. It's like putting all of your wood on the fire all at once, and then thing just blazes away, your eyebrows get singed, and you move away. And so that's what's happening here, is that the red giant stage is very, very bright. And when this happens, the outer planets will probably have a lot of their gas pushed off, ripped off. And some of those ice giants, the ices will melt, like Europa. It may just be a huge water ocean for a short period of time. But the inner planets will be toast. Okay? Even if the Earth does survive this red giant stage, it will not be anything like what it is today. And the oceans will have evaporated long before that as well. So the Earth is just going to be an unrecognizable slag heap after that length of time in this distant epoch in the evolution of our solar system. But eventually, the helium fusion stops, and the star recollapses, but basically now it's just a carbon core. And this is what we call a white dwarf. If the mass of the Sun is less than 1.5 times the mass of our Sun, then the red giant becomes a white dwarf. And so this is what our Sun will become, because it's less than 1.5 times its own mass. Now, white dwarf is about the size of the Earth, but with a density that's about 1 million times the density of water. And so what will happen then is we have carbon in the core, and then the electrons are torn off. And the electrons float up to the surface of the star and create an electron shell. And this shell pressure holds the carbon core and prevents it from collapsing any farther. And so that's it then. The white dwarf then is simply a star like our own Sun in this mass range from 1.5 times the mass of our Sun on down, in which the hydrogen and the helium have run out. What we're left with then is just a carbon core. Electrons are torn off, float to the surface of the star, and then it just kind of fizzles out with time. There's no more fusion reactions. It's a dead star. And the planets may have some kind of an altered orbit around that white dwarf if the planets have been able to survive the red giant stage. However, if the mass of the carbon core is greater than 1.5 times the mass of our sun, then more violent ending is expected for the star. So the star can either blow up, become a supernova, and that produces the kind of heavy elements that we find in our bodies today. Okay, they were produced by other stars that are heavier than our own sun, that eventually exploded because they had basically a carbon core that had a mass that was greater than 1.5 times the mass of our sun. And so that can either cause an explosion, a supernova, or it can cause a catastrophic collapse in which all of the matter of this heavier carbon core eventually, after many fusion reactions, turns into an iron core and then collapses down to become a black hole. So I'll talk about those possibilities next time.